This presentation is one of 6 on non-destructive testing. The topics covered by the other presentations are Introduction to Non-Destructive Testing, Penetrant Testing, Eddy Current Testing, Radiographic Testing, and Ultrasonic Testing. This presentation is an introduction to magnetic particle testing. The material is not intended to train individuals to perform NDT functions, but rather to acquaint them with the NDT equipment and methods that they are likely to encounter. Knowledge of the basic principles and typical applications should enable them to know when to call for help from experts. This presentation will cover the use of magnetic particle inspection to detect various discontinuities in materials which are capable of being magnetized. We will discuss magnetism, ferromagnetic materials, magnetic particle inspection procedures, and show example magnetic particle inspection indications. Magnetic particle inspection relies upon the properties of materials which can be magnetized. Materials which can attract other materials to themselves possess the property of magnetism. These magnetic materials have magnetic lines of force in and around themselves. Magnetic field lines form complete loops, do not cross, follow the path of least resistance, have the same strength, and have a direction which cause poles to attract or repel. This slide illustrates the magnetic field lines around bar magnets using iron particles. The nature of the lines can be seen for a single magnet and for magnets arranged to attract or repel. The magnetic particle inspection method may be applied to ferromagnetic materials. A ferromagnetic material is simply a material which is capable of being magnetized. These materials usually contain iron, nickel, or cobalt. Ferromagnetic materials are made up of regions called magnetic domains in which the magnetic fields of the atoms are aligned. The magnetic domains are randomly oriented in demagnetized materials. Magnetic fields may be used to align the magnetic domains with varying amounts of magnetism. Magnetic particle inspection works because discontinuities in a magnetized material allow the magnetic field to leak outside the material. This flux leakage attracts other magnetic materials, such as iron particles. Finely milled and die-coated iron particles applied to the test article will be attracted and cluster around the leakage fields. This forms an indication directly over the discontinuity. Much like penetrant testing, magnetic particle inspection is a process. The basic steps are also similar. The component is cleaned and magnetized. The magnetic media is applied, and the indications are interpreted. Since the magnetic particles must be free to migrate over the surface of the test article, the part must be clean and dry prior to inspection. Thus, the part must be cleaned of contaminants such as oil and grease. The test article may be magnetized a number of different ways. A permanent magnet or electromagnet may contact the test article. An electrical current may be applied to the test article. A coil of wire encircling the article or a central conductor near the part. There are 2 types of magnetic fields which may be established within the test article. One type has longitudinal lines of force parallel to the long axis. The other type has circular lines of force that run circumferentially around the perimeter. The direction of the lines of force is determined by the direction of the magnetic field used to magnetize the test article. The field created by an encircling coil would create longitudinal magnetism. The magnetic field created by passing a current along the axis of the test article would create circular magnetism, because that is the direction of the magnetic field around a linear current. The longitudinal lines of force exit out one end and enter at the other end, similar to a bar magnet. Circular magnetism, on the other hand, does not exit the part, but simply circle the part. This feature of circular magnetism makes it very difficult to determine if the part is demagnetized or magnetized. It's important to use 2 mutually perpendicular magnetism directions for inspection. The best detection of defects occurs when the lines of force are at right angles to the longest dimension of the defect. Imagine for the moment that the long direction of a defect is parallel to the lines of force. This orientation would not disturb the lines of force at all, and thus not create any flux leakage, which would attract iron particles. When the long direction of a defect is perpendicular to the lines of force, the situation is similar to a broken magnet. In this case, the lines of force do create flux leakage. Basically, the long direction of a defect must be from 45 to 90 degrees relative to the lines of force to be detected. For this reason, test articles are normally magnetized in two mutually orthogonal directions. From what you have learned so far, you should be able to answer the question, which kinds of defect are easily found in the two images? The answer in both cases is the best orientation is for defects perpendicular to the lines of force. The lines of force form from a current through the test article are circular. Thus, the best defect orientation is longitudinal. Conversely, the lines of force from an encircling coil are longitudinal, and thus the best defect orientation is transverse or circumferential. As we mentioned before, the best method to produce longitudinal magnetism is to use an encircling coil. The magnetic field surrounding each turn of the coil is normal to the current direction. The sum of all the individual magnetic fields is along the axis of the coil. The magnetic field strength of the coil also decreases with distance from the conductors in the coil. Thus, the strongest magnetic field is at the inside of the coil's annulus. It is sufficient to simply lie the test article centered on the bottom of a vertical coil, unless the article is relatively long. Another method of producing a longitudinal field is to use permanent magnets, or electromagnetic yokes. The pole pieces of an electromagnetic yoke are adjustable. The pole pieces may be positioned such that the lines of force from one pole to the other would be normal to the flaws of interest. Circular magnetic fields are produced by passing current through the part using a wet horizontal test unit, or contact prods. Using a separate central conductor to carry the current also produces circular magnetic fields. After magnetization, the next step in the process is to apply the magnetic media. The media may be applied either wet or dry. Wet particles are applied by flooding the part with a liquid carrying the particles. Dry particles are lightly dusted on the part. The wet method is more sensitive because the fluid provides greater mobility to the particles. The wet method is sometimes applied during magnetization and sometimes after magnetization, if the test article retains the magnetization. The dry particles are dyed a variety of colors. The color is chosen to produce the greatest contrast against the background. Wet particles may be either visible under white light or fluorescent under ultraviolet or black light. The liquid holds the particles in suspension. The particles are not in solution. Left alone, the particles would settle out due to the force of gravity. Thus, the suspension is kept agitated. One test to assure proper results is to make sure there are enough particles. This may be measured by allowing the particles to settle to the bottom of the special shaped container shown here. Another test is to make sure the ultraviolet light is bright enough and that the particles are still fluorescent. The next stage in the process is interpretation of indications. As with penetrant inspection, the inspector must distinguish between relevant and non-relevant indications. This slide illustrates a crack detected by fluorescent wet particles. This slide illustrates a service-induced crack in a gear. This slide illustrates heat treatment-induced cracks in a drive shaft. This slide shows rather severe service-induced cracks in a splined shaft. This photograph shows a service-induced crack detected using a headshot, that is, current through the shaft inducing circular magnetism which was perpendicular to the axial crack. This is another photograph of a service-induced crack, this time in a large bolt. This photograph shows several cracks near the lube hole of a crankshaft. This photograph shows lack of fusion in a submerged arc weld using visible dry particles. This photograph shows another crack using visible dry particles. The throat and toe cracks in a partially ground weld were detected using visible dry particles. Unlike penetrant inspection, the defects do not necessarily need to be surface connected. Defects near the surface may also cause flux leakage and thus be detectable. The indications will be a little less sharply defined, however. Parts which have been magnetic particle inspected are usually demagnetized after inspection. The residual magnetism might interfere with welding or machining, affect gauges nearby, or attract abrasive particles, which would cause increased wear. Demagnetization reduces and reverses the residual magnetic field in an attempt to create a scrambled or random orientation of the magnetic domains. This is done by placing the part in a magnetic field which alternates the direction of the applied magnetization field while continuously decreasing the strength of the field as well. This process takes some time. Circular magnetism is the most difficult to reverse and to measure. Since longitudinal magnetism is easier to remove, a circularly magnetized part may be magnetized longitudinally to create the correct orientation before being demagnetized. One method of demagnetization is to simply pass the part through an AC encircling coil. The AC excitation continuously reverses the magnetization direction, while the field strength increases and then decreases as the part enters and leaves the coil. Another method is to use the head shot repeatedly, changing both the direction and strength until the magnetism is removed. Magnetic particle inspection has the following advantages. Magnetic particle inspection can detect both surface and near subsurface defects. The method can easily inspect parts with irregular shapes. Pre-cleaning of components is not as critical as it is for penetrant and some other inspection methods. Unlike penetrant inspection, most contaminants within a flaw will not hinder flaw detection. The method is fast and indications are visible directly on the specimen surface. The method is relatively low cost compared to many other NDT methods. Finally, the method is very portable when used with battery-powered equipment. The limitations of magnetic particle inspection include non-ferrous materials such as aluminum, magnesium, or most stainless steels cannot be inspected because they cannot be magnetized. Inspection of large parts may require the use of equipment with special power requirements. Some parts may require removal of coating or plating to achieve the desired inspection sensitivity. The method has limited subsurface discontinuity detection capabilities. The maximum depth sensitivity is approximately 0.6 of an inch under ideal conditions. Post-cleaning and post-demagnetization is often necessary. Finally, the alignment between magnetic flux and defect orientation is important. The following glossary of terms defines some of the terms used in magnetic particle inspection. Black light is ultraviolet light which is filtered to produce a wavelength of approximately 365 nanometers. Black light will cause certain materials to fluoresce. A central conductor is an electrically conductive bar usually made of copper used to introduce a circular magnetic field in a test specimen. A coil is an electrical conductor such as a copper wire that is wrapped in several loops that are brought close to one another to form a strong longitudinal magnetic field. Discontinuity is an interruption in the structure of the material, such as a crack. Ferromagnetic describes a material such as iron, nickel, and cobalt, or one of their alloys, that is strongly attracted to a magnetic field. Heads describe the electrical contact pads on a wet horizontal magnetic particle inspection machine. The part to be inspected is clamped and held in place between the heads, and a shot of current is sent through the part from the heads to create a circular magnetic field in the part. A leakage field is a disruption in the magnetic field. This disruption must extend to the surface of the part for particles to be attracted. Non-relevant indications are indications produced due to some intended design feature of a specimen, such as keyways, splines, or press fits. Prods are two electrodes usually made of copper or aluminum that are used to introduce current into a test part. This current in turn creates a circular magnetic field where each prod touches the part. It's similar in principle to a welding electrode and ground clamp. Relevant indications are indications produced from something other than a design feature of a test specimen. Cracks, stringers, or laps are examples of relevant indications. A suspension is a bath created by mixing particles with either oil or water. A yoke is a horseshoe magnet used to create a longitudinal magnetic field. Yokes may be made from permanent magnets or electromagnets.